Take a moment and look at your hand. It contains roughly 100 trillion atoms, more atoms than there are stars in our entire galaxy. Now prepare yourself for this. Our galaxy is just a tiny speck compared to the largest structures we've discovered in the universe. We're about to journey from Earth to the absolute edge of what exists, discovering objects so vast that light itself needs billions of years to cross them. By the end of this journey, you'll understand what truly is the largest thing in the universe, and the answer might not be what you expect. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Your support helps me explore the biggest questions about our universe. Now let's begin. When we talk about the largest thing in the universe, we need to first understand what large even means on cosmic scales. On Earth, Mount Everest seems impossibly huge at 8.8 kilometers high, but Earth itself, at 12,700 kilometers across, dwarfs any mountain. Jupiter could swallow Earth 1,300 times over. Our Sun could contain 1 million Earths, and yet our Sun is just an average star among 400 billion in our galaxy. The Milky Way galaxy spans 100,000 light-years across. To understand this distance, remember that light travels at 300,000 kilometers per second, fast enough to circle Earth 7 times in 1 second. Yet light needs 100,000 years to cross our galaxy. If our solar system were the size of a coin, the Milky Way would be as large as the United States. But here's where our journey truly begins. In 1924, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to prove that Andromeda wasn't just a nebula within our galaxy, it was an entire galaxy itself, 2.5 million light-years away. Suddenly, the universe became unimaginably larger. What we thought was everything turned out to be just one island in a cosmic ocean. Modern telescopes have revealed the true scale of our cosmic neighborhood. The local group, which contains our Milky Way, Andromeda, and about 80 smaller galaxies, spans 10 million light-years. But even this collection of galaxies is dwarfed by larger structures. The Virgo cluster, the nearest large galaxy cluster, contains over 1,300 galaxies and spans 15 million light-years. The Hubble Space Telescope, launched in 1990, revolutionized our understanding of cosmic scales. Its deep-field images revealed that what appeared to be empty patches of sky actually contained thousands of galaxies, each with hundreds of billions of stars. The James Webb Space Telescope, operational since 2022, has pushed even further, showing us galaxies from when the universe was just a few 100 million years old. But galaxies don't exist in isolation. They're connected by vast cosmic filaments made of dark matter and gas, forming what astronomers call the cosmic web. The Sloan Digital Sky Survey, which began in 2000, has mapped millions of galaxies, revealing this web-like structure. Galaxies align along filaments that stretch for hundreds of millions of light-years, with vast empty voids between them. In 2003, astronomers discovered the Sloan Great Wall, a cosmic structure that shattered all previous records. This wall of galaxies stretches 1.37 billion light-years across, about 1/60th the diameter of the observable universe. To put this in perspective, if Earth were a grain of sand, the Sloan Great Wall would be larger than Earth itself. The discovery process reveals how we push the boundaries of knowledge. The 2-degree Field Galaxy Redshift Survey used the Anglo-Australian telescope to measure distances to over 200,000 galaxies. By analyzing their redshift, how their light stretches as they move away from us, astronomers could create 3-dimensional maps of structures larger than anything previously imagined. But we were just getting started. In 2013, astronomers using data from multiple surveys discovered the Hercules Corona Borealis Great Wall. This structure spans 10 billion light-years, more than 1/10 the the diameter of the observable universe. Its discovery challenged our understanding of how such massive structures could form in the time since the Big Bang. The scale is so vast it challenges comprehension. Light from one end of the Hercules Corona Borealis Great Wall would take 10 billion years to reach the other end. When that light began its journey, our solar system didn't exist. Earth wouldn't form for another 5 billion years. The first simple life was still 8 billion years in the future. These discoveries came from gamma-ray burst observations. The Swift satellite and Fermi Gamma-ray Space Telescope detected unusual clustering of these cosmic explosions in the Hercules and Corona Borealis regions. Gamma-ray bursts are the most energetic events in the universe, visible across billions of light-years, making them perfect tracers of distant cosmic structure. But how do these massive structures form? Computer simulations like the Millennium simulation and the Illustris project use supercomputers to model how gravity shapes matter over billions of years. Starting from tiny quantum fluctuations in the early universe, gravity pulls matter together, creating a cosmic web of filaments and voids. Dark matter, which makes up 85% of all matter, provides the gravitational scaffolding that ordinary matter follows. The Planck satellite, which mapped the cosmic microwave background from 2009 to 2013, showed us the seeds of these structures. Tiny temperature variations in the infant universe, just 30 parts per million, grew over billions of years into the massive walls and voids we see today. It's like watching ripples in a pond grow into tsunami waves, except the pond is the entire universe, and the process takes 13.8 billion years. Recent observations have revealed even larger structures. The Boss Great Wall, discovered in 2016, spans 1 billion light-years. The Saraswati Supercluster, discovered in 2017, contains over 40,000 galaxies with a total mass of 20 million billion times our Sun. Each discovery pushes our understanding of what large means in the universe. But size isn't just about distance, it's also about mass and gravitational influence. The Shapley supercluster, located 500 million light-years away, contains such an enormous concentration of galaxies that its gravity affects the motion of galaxies hundreds of millions of light-years away, including our own Milky Way. We're literally falling toward it at 600 kilometers per second. There's something massive lurking in the cosmos, so enormous that it's pulling hundreds of thousands of galaxies toward it, including our own. Astronomers call it the Great Attractor, and it represents one of the most mysterious large-scale structures in the universe. Hidden behind the dense star fields of our own galaxy, this gravitational anomaly affects everything within hundreds of millions of light-years, creating vast rivers of galaxies flowing through space. The discovery of the Great Attractor began in the 1970s when astronomers noticed something odd. Galaxies weren't just moving apart due to universal expansion, they also had peculiar velocities, moving in specific directions as if pulled by invisible hands. Our local group, including the Milky Way and Andromeda, is racing towards something in the direction of the Centaurus constellation at 600 kilometers per second. The Seven Samurai, a team of astronomers in the 1980s, mapped these cosmic flows using innovative techniques. They measured distances to elliptical galaxies using the Faber-Jackson relation and spiral galaxies using the Tully-Fisher relation. These methods revealed that vast regions of space were moving coherently, like rivers flowing toward an unseen ocean. The problem was we couldn't see what was pulling us. The Great Attractor lies in the zone of avoidance, the region of sky blocked by our galaxy's disk. The Milky Way's dust and billions of stars create a blind spot exactly where we need to look. It's like trying to see What's behind a bright searchlight pointed directly at your eyes? X-ray astronomy provided the breakthrough. The Rosat satellite in the 1990s could peer through the galactic dust by detecting X-rays from hot gas in galaxy clusters. These observations revealed the Norma cluster, a massive concentration of galaxies near the Great Attractor's predicted location. But even this wasn't the whole story. In 2016, the Parkes Radio Telescope in Australia conducted the NRAO VLA Sky Survey, mapping galaxies behind the Milky Way using radio waves that penetrate dust. They discovered over 800 galaxies in the zone of avoidance, revealing a complex structure of clusters and superclusters contributing to the Great Attractor's pull. But then came a bigger surprise. The Great Attractor itself is moving, pulled by something even larger. The Shapley supercluster, located beyond the Great Attractor, contains over 8,000 galaxies in a volume of space spanning 200 million light-years. This concentration of matter is so massive that it dominates the gravitational landscape for 500 million light-years in every direction. Recent data from the Cosmic Flows project has mapped these motions in unprecedented detail. Using the Hubble Space Telescope and ground-based observatories, astronomers measured precise distances to thousands of galaxies. The resulting maps show cosmic flows like ocean currents, with galaxies streaming along invisible gravitational channels toward the largest concentrations of matter. The scale of these flows is staggering. The Laniakea supercluster, identified in 2014, spans 520 million light-years and contains 100,000 galaxies, including our own. The name Laniakea means immense heaven in Hawaiian, chosen to honor the Polynesian navigators who used the stars to traverse the Pacific. Just as they mapped ocean currents, we're now mapping the flows of galaxies through space. Laniakea's discovery changed our cosmic address. We're not just in the Milky Way, in the local group, in the Virgo cluster. We're part of this immense structure, connected by gravitational threads to galaxies hundreds of millions of light-years away. The boundary of Laniakea is defined by cosmic flows. Galaxies inside flow toward its center, while those outside flow toward other superclusters. But even Laniakea might not be the largest coherent structure. The Pisces-Cetus supercluster complex spans 1 billion light-years and includes multiple superclusters. These structures form a vast network of cosmic matter, with filaments of galaxies stretching between massive nodes like a three-dimensional spiderweb spanning the observable universe. The Dark Energy Survey, using the Blanco telescope in Chile, has revealed how these structures evolve. By observing millions of galaxies at different distances and therefore different times in cosmic history, we can watch structures grow over billions of years. Small fluctuations in the early universe grew into the massive walls and superclusters we see today. Understanding these large structures requires grappling with dark matter and dark energy. Dark matter provides the invisible scaffolding that ordinary matter follows, creating the cosmic web. Dark energy, discovered through observations of distant supernovae in 1998, works against gravity, accelerating cosmic expansion and limiting how large structures can grow. The South Pole Telescope and Atacama Cosmology Telescope study these structures using the Sunyaev-Zeldovich effect. When cosmic microwave background photons pass through galaxy clusters, hot gas boosts their energy, creating shadows that reveal massive structures even at extreme distances. These observations show that the largest structures formed earlier than expected, challenging our models of cosmic evolution. Computer simulations help us understand what we observe. The Eagle simulation uses supercomputers to model how galaxies form and cluster over cosmic time. The Illustris TNG project simulates volumes of space over 1 billion light-years across, tracking the formation of millions of galaxies. These simulations reproduce the cosmic web we observe, validating our understanding while revealing new mysteries. One puzzle is the missing baryon problem. When we add up all the visible matter in galaxies, it's only about half of what should exist based on Big Bang nucleosynthesis. Recent observations using fast radio bursts as cosmic probes suggest this missing matter hides in warm hot gas, filling the cosmic web's filaments. Matter that's part of the largest structures but nearly invisible to traditional observations. The eROSITA X-ray telescope, launched in 2019, is conducting an all-sky survey to map this hidden matter. Early results reveal hot gas filaments connecting galaxy clusters, confirming that the largest structures contain far more than just the galaxies we see. These gaseous filaments, millions of degrees hot and millions of light-years long, are themselves among the largest coherent structures in the universe. Gravitational lensing provides another window into large-scale structure. When light from distant galaxies passes by massive structures, gravity bends its path. The Dark Energy Survey and upcoming Vera Rubin Observatory use this effect to map dark matter distributions across billions of light-years, revealing structures invisible to conventional telescopes. The largest structures in the universe aren't random collections of galaxies, they're organized into an intricate pattern called the cosmic web. This vast network of dark matter filaments, gas clouds, and galaxies spans the entire observable universe, creating a structure so large that we're only now beginning to understand its true scale. Modern surveys have revealed that what we see, the galaxies and stars, is just the tip of an enormous cosmic iceberg. The cosmic web's discovery came gradually. In the 1980s, the Harvard-Smithsonian Center for Astrophysics conducted the first large-scale galaxy survey. Margaret Geller and John Hutra created slices of the universe, mapping galaxy positions in wedge-shaped regions. What they found shocked the astronomical community. Galaxies weren't distributed randomly but formed bubble-like structures with vast empty voids. The 2-micron all-sky survey, completed in 2003, used infrared telescopes to peer through cosmic dust and map over 1.5 million galaxies. This revealed that the cosmic web extends in all directions with no special center or edge. We're embedded in this vast network like a single neuron in a cosmic brain spanning billions of light years. Dark matter forms the skeleton of this cosmic web. Although it makes up 85% of all matter, we can't see it directly. The Canada-France-Hawaii Telescope Legacy Survey used gravitational lensing to map dark matter across large regions of sky. These dark matter maps show a vast network of invisible filaments, with ordinary matter following their gravitational guidance like rivers following valleys. If you're fascinated by these massive cosmic structures and want to understand what powers them, check out my video called "What is the Most Powerful Thing in the Universe?", where I explore everything from supernovas that forge the elements in these structures to the dark energy that shapes their evolution. You'll discover how gamma-ray bursts, quasars, and even the Big Bang itself contribute to building these larger structures. It perfectly complements what we're discussing about cosmic scale. The link is in the description and on the card above. Now let's continue exploring these vast structures. The Millennium simulation, run on supercomputers in Germany, modeled 10 billion dark matter particles over cosmic time. Starting from tiny fluctuations just after the Big Bang, the simulation showed how gravity weaves matter into the cosmic web. The results matched our observations so well that astronomers use these simulations to understand structures too large to observe completely. Recent discoveries have revealed structures that challenge our understanding of the cosmic web's limits. The Boss Great Wall, discovered using the Baryon Oscillation Spectroscopic Survey, contains over 800,000 galaxies spread across 1 billion light-years. But even more puzzling is how uniform these structures appear when viewed at the largest scales. The cosmological principle states that the universe should look the same in all directions when averaged over large enough scales. But how large is large enough? The Sloan Digital Sky Survey found that homogeneity emerges at scales around 300 million light-years. Below this scale, we see the cosmic web structure. Above it, the universe looks smooth, like viewing Earth from space where mountains and valleys disappear into a smooth sphere. Voids, the empty spaces between filaments, are structures in their own right. The Boötes supervoid, discovered in 1981, spans 330 million light-years with very few galaxies inside. It's so empty that if the Milky Way were at its center, we wouldn't have discovered other galaxies until the 1960s, when telescopes became powerful enough to see across the entire void. The KBC void, in which we might actually live, could be 2 billion light-years across. This local underdensity would explain some puzzling observations like discrepancies in measurements of cosmic expansion rate. Living in a cosmic void would mean our local universe expands slightly faster than denser regions, affecting our measurements of cosmic parameters. But the cosmic web isn't static, it's evolving. The Dark Energy Spectroscopic Instrument at Kitt Peak Observatory is creating the largest three-dimensional map of the universe ever made. By measuring 40 million galaxies and quasars, it's revealing how the cosmic web has grown and changed over 11 billion years of cosmic history. Quasars, powered by supermassive black holes billions of times our Sun's mass, serve as beacons illuminating the cosmic web. As their light travels through space, it passes through clouds of hydrogen gas in the cosmic web's filaments. This creates absorption lines called the Lyman alpha forest, revealing the distribution of matter between us and the quasar. It's like using cosmic lighthouses to map an invisible ocean. The Climato survey used the Keck Observatory to create three-dimensional maps of the cosmic web using this technique. They revealed filaments of gas stretching between galaxies, confirming that the cosmic web contains far more than just the galaxies we see. These gaseous filaments contain most of the universe's ordinary matter, hiding in forms too diffuse to see directly. Galaxy clusters, the largest gravitationally bound structures, sit at the nodes where cosmic filaments meet. The Coma cluster, containing over 1,000 galaxies, spans 20 million light-years and weighs as much as a quadrillion suns. But even these massive clusters are just nodes in the larger cosmic web, like cities connected by highways of dark matter and gas. The Planck satellite's observations revealed something unexpected about the cosmic web. By measuring the cosmic microwave background, light from when the universe was only 380,000 years old, Planck showed that the seeds of the cosmic web were present from the universe's infancy. Tiny quantum fluctuations, stretched to cosmic scales by inflation, became the blueprint for the largest structures we see today. But there's a limit to how large structures can grow. Dark energy, the mysterious force accelerating cosmic expansion, prevents structures larger than about 1.2 billion light-years from forming. As the universe expands faster, gravity can't pull matter together over larger distances. We're living in the era when the largest structures that will ever exist are forming right now. The Euclid Space Telescope, launched in 2023, is designed specifically to map the cosmic web and understand dark energy. Using visible and near-infrared instruments, it will observe billions of galaxies, creating the most detailed map of the cosmic web structure and evolution. This will help us understand not just what the largest structures are, but why they're limited to their current sizes. Future surveys promise even greater revelations. The Vera Rubin Observatory, beginning operations soon, will photograph the entire southern sky every few nights, tracking how the cosmic web evolves in real time. The square-kilometre Array Radio Telescope will map hydrogen gas throughout the cosmic web, revealing structures invisible to optical telescopes. As we push deeper into the cosmos, we encounter structures so vast that they challenge the fundamental assumptions of cosmology. These gigantic formations span significant fractions of the observable universe itself, raising profound questions. How can structures this large exist? How did they form in the limited time since the Big Bang? And do they represent the absolute limit of cosmic organization? Or is there something even larger waiting to be discovered? The giant arc, discovered in 2021, represents one of the most puzzling large-scale structures ever found. Spanning 3.3 billion light-years, about 1/15 of the observable universe's radius, it consists of galaxies, galaxy clusters, and gas forming a nearly symmetrical arc in the constellation Borealis. Alexia Lopez, a PhD student at the University of Central Lancashire, discovered it while analyzing light from 40,000 quasars captured by the Sloan Digital Sky survey. What makes the giant arc particularly mysterious is that it shouldn't exist according to our current understanding. The cosmological principle suggests that at scales above 300 million light-years, the universe should appear uniform. Yet the giant arc is 10 times larger than this theoretical limit, and it shows a coherent structure that seems to defy random distribution. Even more remarkably, Lopez discovered another massive structure nearby, the Big Ring, spanning 1.2 billion light-years. Finding two such enormous structures in the same region of sky, at the same distance from Earth, suggests they might be related, possibly parts of an even larger, unknown structure. These discoveries are forcing cosmologists to reconsider whether our understanding of the universe's large-scale structure is complete. The Huge Large Quasar Group, discovered by Roger Close in 2013, presents another challenge to cosmological theories. This collection of 73 quasars spans 4 billion light-years, making it one of the largest known structures. Quasars are among the brightest objects in the universe, powered by matter falling into supermassive black holes, making them visible across billions of light-years and perfect traces of large-scale structure. The existence of the huge LQG violates the theoretical maximum size for cosmic structures. According to the Yadav, Bagla, and Kandai principle, gravitationally bound structures shouldn't exceed 1.2 billion light-years. Yet the huge LQG is more than 3 times this limit. Either our theories need revision, or these structures aren't gravitationally bound in the traditional sense. The cosmic web itself might have larger scale organization than previously thought. The South Pole Wall, discovered in 2020, stretches 1.4 billion light-years across and sits just 500 million light-years from Earth. The fact that such an enormous structure remained hidden until recently, practically in our cosmic backyard, suggests that even larger structures might be waiting to be discovered. Daniel Pomerade and his team discovered the South Pole Wall using a technique called peculiar velocity analysis. By measuring how galaxies move relative to cosmic expansion, they can map gravitational influences and reveal structures hidden behind the zone of avoidance, the region blocked by our galaxy. This technique has revealed that what we see directly is only part of the cosmic structure story. But size isn't just about physical extent, it's also about gravitational influence. The Shapley supercluster, while only spanning 200 million light-years, contains such an enormous concentration of matter that it affects galaxy motions over 1 billion light-years away. Its gravitational pull is so strong that it's redirecting the cosmic flow of hundreds of thousands of galaxies, including our own. Recent observations have revealed structures that seem to transcend traditional classification. The Telescope Array project in Utah, detecting ultra-high energy cosmic rays, found that these particles seem to arrive preferentially from a particular region of sky. This hotspot suggests a structure or phenomenon spanning billions of light-years that's accelerating particles to energies that shouldn't be possible given the cosmic microwave background's limiting effect. The Perseus-Pisces supercluster represents another category of enormous structure, a chain of galaxy clusters stretching 300 million light-years. Unlike more spherical superclusters, it forms an elongated filament, one of the largest coherent structures in the nearby universe. Radio observations reveal that this isn't just a chance alignment, but a physically connected structure with gas bridges between clusters. The cold spot in the cosmic microwave background might indicate the largest structure of all, a supervoid spanning up to 1 billion light-years. Discovered by the Wilkinson Microwave Anisotropy Probe and confirmed by Planck, this region shows a temperature about 70 microkelvin colder than average. The leading explanation is an enormous void that light must traverse, losing energy as the universe expands during its journey. Computer simulations struggle to reproduce these largest observed structures. The Horizon Run simulations, using billions of particles to model cosmic evolution, rarely produce structures as large as what we observe. This discrepancy might mean we're missing something fundamental about structure formation, or these structures might be statistical flukes in an otherwise uniform universe. The concept of the observable universe itself represents the ultimate large-scale structure. With a diameter of 93 billion light-years, it encompasses everything we can possibly see. But this isn't a physical structure. It's an observational limit defined by the finite speed of light and age of the universe. Each observer in the universe has their own observable universe, overlapping but not identical to ours. Beyond our observable universe might lie structures we'll never see. Inflation theory suggests the total universe is at least 10 to the 23 times larger than what we observe, possibly infinite. In such a vast cosmos, structures larger than our entire observable universe could exist forever beyond our ability to detect or study them. The multiverse hypothesis takes this even further. If our universe is one bubble in an infinite foam of universes, then the largest structure might be the multiverse itself, an infinite collection of universes, each with different physical laws, separated by eternally inflating space. While currently untestable, this represents the ultimate limit of thinking about cosmic structure. Observational techniques continue to improve, revealing ever larger structures. The 500-meter aperture spherical telescope in China can detect hydrogen gas at unprecedented distances. The square-kilometer array under construction in Australia and South Africa will map billions of galaxies, potentially revealing structures spanning the entire observable universe. We've journeyed from galaxies to superclusters, from great walls to mysterious arcs spanning billions of light-years, but now we must confront the ultimate question: what is the absolute largest thing we can observe? The answer brings us to the observable universe itself, not just as a collection of structures, but as a single, unified entity with defined boundaries. This cosmic horizon represents the absolute limit of what we can ever see or know, making it, in a very real sense, the largest thing that exists from our perspective. The observable universe has a precise definition. It's the sphere of space centered on Earth from which light has had time to reach us since the Big Bang. This isn't because Earth is special. Every point in space has its own observable universe, like overlapping bubbles in an infinite foam. An alien civilization in a galaxy 10 billion light-years away sees a different observable universe, with regions we'll never observe. The radius of our observable universe is approximately 46.5 billion light-years, giving it a diameter of 93 billion light-years. This might seem confusing. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? The answer lies in cosmic expansion. While light from distant objects has been traveling for billions of years, space itself has been stretching, carrying those objects even farther away. The particle horizon marks the absolute boundary of our observable universe. It represents the maximum distance from which particles could have traveled to reach us since the Big Bang. No signal, no light, no information from beyond this horizon can ever reach us. It's not just that we haven't seen beyond it. It's physically impossible for us to ever see beyond it, no matter how powerful our telescopes become. But the observable universe isn't static. It's growing. Every second, the particle horizon expands by 1 light second in all directions as light from slightly more distant regions finally reaches us. Paradoxically, while our observable universe grows, the number of galaxies we can see is decreasing. Dark energy's acceleration means distant galaxies are crossing another boundary, the cosmic event horizon, beyond which their light will never reach us. The Hubble ultra-deep field, captured over 11 days of observation, revealed approximately 10,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. Extrapolating across the entire sky suggests our observable universe contains over 2 trillion galaxies. Each galaxy averages hundreds of billions of stars, meaning the observable universe contains roughly 10 to the 24 stars, a septillion suns. But counting objects misses the profound unity of the observable universe. Everything we see shares a common origin in the Big Bang. The cosmic microwave background radiation discovered by Arno Penzias and Robert Wilson in 1964 provides direct evidence of this unity. This faint glow coming from every direction is the cooled remnant of the universe's hot beginning, linking every point in our observable universe to a common moment of creation. The Planck satellite's map of the cosmic microwave background reveals the observable universe's baby picture, how matter was distributed when the universe was only 380,000 years old. These tiny temperature fluctuations, just 30 parts per million, grew into all the structures we see today. Every galaxy, star, and planet emerged from these primordial ripples, making the observable universe a single, evolving system. Mass estimates for the observable universe are staggering. The total mass energy, including dark matter and dark energy, is approximately 10 to the 53 kilograms. That's 10 followed by 53 zeros, a number so large it defies comprehension. If you converted the entire observable universe to energy using Einstein's E equals mc squared, it would be 10 to the 70 joules, enough to power our sun for 10 to the 60 years. The observable universe's geometry tells us about the total universe beyond our horizon. Measurements from the Planck satellite show space is flat to within 0.4% accuracy. This flatness suggests the total universe is at least 250 times larger than what we observe, and possibly infinite. We're seeing only a tiny fraction of all that exists. Dark energy comprises 68% of the observable universe's energy density, dark matter 27%, and ordinary matter just 5%. This means everything we see, every star, planet, and galaxy, represents less than 1/20th of our observable universe's content. The largest thing we can observe is mostly invisible, dominated by mysterious components we barely understand. The observable universe's structure shows remarkable uniformity at the largest scales. The Baryon oscillation spectroscopic survey measured galaxy distributions across billions of light-years, confirming that the universe becomes homogeneous at scales above 300 million light-years. This uniformity supports the cosmological principle and suggests the observable universe is a representative sample of the larger cosmos. Time adds another dimension to the observable universe's size. When we look at distant objects, we see them as they were billions of years ago. The most distant galaxy observed, GN-Z11, appears as it was 13.4 billion years ago, just 400 million years after the Big Bang. Our observable universe is thus not just a sphere in space, but a cone in space-time, with us at the tip and the Big Bang at the base. The James Webb Space Telescope is pushing these boundaries further. Its infrared vision can detect galaxies from when the universe was just a few hundred million years old, revealing how the first structures formed. Each new discovery adds to our understanding of the observable universe as a single, evolving entity, growing from smooth beginnings to the complex cosmic web we see today. But the observable universe faces a lonely future. In approximately 100 billion years, cosmic acceleration will have pushed all galaxies outside our local group beyond the cosmic event horizon. Future civilizations will see an observable universe containing only our merged galaxy, surrounded by darkness. The cosmic microwave background will have redshifted beyond detectability. They'll have no direct evidence of the Big Bang or cosmic expansion. This makes our current epoch special. We live at a time when the observable universe still contains evidence of its origin and evolution. We can see the cosmic web, measure expansion, and trace our cosmic history. Future observers will inhabit a simpler, observable universe, unable to discover what we know today. We're privileged to see the universe at its most revealing moment. As vast as our observable universe is, it represents only what we can see, not necessarily all that exists. Modern cosmology suggests the total universe extends far beyond our cosmic horizon, possibly infinitely. This raises profound questions. If structures larger than our observable universe exist, how would we know? What theoretical limits constrain the size of cosmic structures? And what does it mean for something to be larger than everything we can possibly observe? Inflation theory, proposed by Alan Guth in 1980, suggests our observable universe is a tiny fraction of a much larger whole. During inflation, space expanded by a factor of at least 10 to the 26 in about 10 to the negative 32 seconds. This exponential expansion would make the total universe at least 10 to the 23 times larger than what we observe. And that's the conservative estimate. If inflation was eternal, as many models suggest, the total universe could be infinite. In eternal inflation, most of space continues expanding exponentially forever, with only small regions stopping to form pocket universes like ours. Our observable universe would be an infinitesimally small part of one pocket universe, itself a tiny bubble in an infinite inflating foam. The quilted multiverse represents one type of structure beyond our observable universe. If space is infinite and matter is distributed roughly uniformly, then identical copies of our observable universe must exist. The numbers are mind-boggling, but within a volume of 10 to the 10 to the 115 meters, quantum mechanics suggests you'd find an exact duplicate of our observable universe, including identical copies of Earth and everyone on it. But these duplicates aren't connected structures, they're separated by unimaginable distances. The scale is so vast that writing the distance in meters would require more digits than there are particles in our observable universe. These regions can never communicate or influence each other, raising philosophical questions about whether disconnected duplicates constitute a single structure. String theory suggests another type of structure beyond observation, the landscape multiverse. With 10 to the 500 possible configurations of extra dimensions and physical constants, string theory predicts a vast landscape of possible universes. These wouldn't just be copies, but fundamentally different realities with different laws of physics, separated by quantum tunneling barriers rather than distance. The holographic principle, developed from black hole physics, suggests a radical limit on structure size. It states that the maximum information content of any region is proportional to its surface area, not volume. Applied cosmologically, this might mean the observable universe's two-dimensional boundary contains all the information about its three-dimensional interior, limiting how complex structures can become. Computer simulations help us understand theoretical limits. The largest simulations, like the Uchu simulation completed in 2021, model volumes spanning billions of light-years with trillions of particles. These show that structure formation has natural limits. Dark energy prevents structures larger than about 1.2 billion light-years from forming, regardless of the universe's total size. The end of greatness marks where the universe transitions from structured to smooth. At scales beyond 300 million light-years, the cosmic web's patterns give way to statistical uniformity. This isn't just observational, it's predicted by the cosmological principle and confirmed by every large-scale survey. No matter how large the total universe, this uniformity should persist. Quantum mechanics might impose ultimate limits on structure. The de Sitter horizon related to dark energy suggests that regions separated by more than about 16 billion light-years can never communicate, even given infinite time. This creates isolated island universes that evolve independently, preventing truly universe-spanning structures from forming or maintaining coherence. The anthropic principle offers another perspective on cosmic limits. We observe structures of certain sizes because only universes with such structures can support observers. If physical constants were different, allowing larger or smaller maximum structures, we wouldn't be here to observe them. Our observable universe's properties might be typical of regions that can produce conscious observers. Black hole cosmology presents a mind-bending possibility. Some theories suggest our universe exists inside a black hole in a higher dimensional space. If true, the largest structure would be the black hole containing our entire universe. This would explain the Big Bang, the formation of the black hole, and why we can't see beyond certain limits, the event horizon. The conformal cyclic cosmology proposed by Roger Penrose suggests the universe undergoes infinite cycles, with each aeon ending in a state indistinguishable from the next aeon's beginning. In this model, structures from previous aeons might influence our universe through gravitational waves or other subtle effects, making the largest structure the infinite sequence of cosmic aeons. Brain world scenarios from string theory propose our three-dimensional universe is a membrane floating in higher dimensional space. Other brains, entire other universes, might float nearby in the higher dimensions, occasionally colliding with ours. The largest structure would be the higher dimensional space containing all these universe brains. Recent observations hint at structures beyond standard models. The dark flow, a controversial observation suggesting galaxies moving coherently toward a point beyond our observable universe, might indicate massive structures beyond our horizon. While disputed, such observations remind us that surprises may await as our observations improve. The cosmic web's filaments might extend beyond our observable universe, connecting regions we'll never see. Simulations suggest these filaments could span hundreds of billions of light-years in an infinite universe, dwarfing anything we observe. We see only local segments of potentially infinite structures, like examining a few inches of an endless rope. Future observations might reveal hints of trans-horizon structures. Patterns in the cosmic microwave background could encode information about regions beyond our particle horizon. Gravitational waves from inflation might carry signals from parts of the universe we'll never see with light. These subtle clues could reveal whether structures larger than our observable universe exist. The question, what is the largest thing in the universe, ultimately depends on what we mean by universe. In our observable universe, it's the universe itself as a unified whole. In the total universe, structures might exist beyond our comprehension. And in the multiverse, the question might be meaningless, like asking for the largest number in an infinite set. In our search for the largest things in the universe, we've focused on concentrations of matter, walls, filaments, and clusters. But what if the largest structures are defined not by what they contain, but by what they lack? The cosmic voids, vast regions nearly empty of galaxies, represent some of the largest individual structures in the universe. These enormous bubbles of emptiness might tell us more about the universe's large-scale organization than all the galaxy clusters combined. The discovery of cosmic voids revolutionized our understanding of universal structure. In 1981, Robert Kirshner and his team discovered the Boötes void, a roughly spherical region containing very few galaxies. Spanning 330 million light-years, it was so empty that astronomers initially thought their observations were flawed. Where thousands of galaxies should exist, they found only about 60. The local void presents an even more intriguing mystery. We appear to live near the edge of an enormous void, possibly 2 billion light-years across. The KBC void, named after astronomers Keenan, Barger, and Cowie, might explain some puzzling observations about our cosmic neighborhood. Living in an underdense region would affect how we measure cosmic expansion, potentially resolving tensions between different measurement methods. Voids aren't completely empty, they contain diffuse gas, dark matter, and occasional galaxies. But their density is about 1/10 the cosmic average. If the universe were an ocean, voids would be vast bubbles of air, with galaxies clinging to the bubble walls. The galaxies inside voids are typically smaller and fainter than those in dense regions, evolving differently due to their isolation. The Eridanus supervoid associated with the cosmic microwave background cold spot might be the largest void we've detected. Spanning up to 1 billion light-years, it contains far fewer galaxies than expected. Light crossing this void loses energy due to the integrated Sachs-Wolf effect, creating the observed temperature depression. This void is so large it challenges our understanding of how such empty regions can form. Computer simulations reveal how voids grow. Starting from tiny, underdense regions in the early universe, voids expand as gravity pulls matter towards surrounding, denser regions. It's like reverse structure formation. Instead of matter clumping together, it flows away from void centers. Over billions of years, small voids merge to create the enormous bubbles we observe today. The VMOS Public Extragalactic Redshift Survey mapped thousands of voids, revealing they're not randomly distributed, but form their own patterns. Voids tend to be roughly spherical, with typical diameters of 100 to 200 million light-years. The largest voids result from multiple smaller voids merging, creating irregular shapes that can span over 1 billion light-years. Void galaxies offer unique laboratories for studying galaxy evolution. Isolated from the gravitational harassment common in dense regions, void galaxies evolve more slowly. They tend to be gas-rich spirals with active star formation, resembling younger versions of galaxies in denser regions. Studying them reveals how galaxies would evolve without constant interactions with neighbors. The void phenomenon extends to dark matter. Weak gravitational lensing surveys show that dark matter is also depleted in voids, though not as dramatically as visible matter. This suggests voids formed from primordial underdensities that affected all types of matter. The dark matter web has its own voids, roughly coinciding with galaxy voids but with smoother boundaries. Recent discoveries suggest voids might be even larger than we thought. The BOSS survey found evidence for supervoids spanning over 1 billion light-years. These structures are so large that light hasn't had time to cross them more than a few times since the Big Bang. Their existence pushes against theoretical limits for how large voids can grow in the time available. Voids affect cosmic flows on enormous scales. Matter streams away from void centers toward surrounding walls and filaments, creating coherent velocity patterns spanning hundreds of millions of light-years. The local void pushes our local group toward the Virgo cluster at about 200 kilometers per second, contributing to our overall motion through space. The cosmic web can be understood as the negative space between voids. If voids are bubbles, the cosmic web is the soap film between them. This perspective inverts our usual thinking. Instead of voids being absence of structure, they're the primary structure, with matter confined to their boundaries. The universe is more void than substance. Void hierarchy reveals multiple scales of organization. Small voids, tens of millions of light-years across, nest inside larger voids spanning hundreds of millions of light-years. The largest supervoids contain multiple levels of substructure. It's like foam within foam, with structure at every scale from the smallest voids to the largest supervoids. The Millennium simulation and its successors show void evolution over cosmic time. Early in the universe, matter was more uniformly distributed with smaller density contrasts. As gravity amplified these contrasts, voids expanded and deepened. In the future, dark energy will accelerate void growth until they dominate the universe's volume even more than today. Voids might hold clues to fundamental physics. Their emptiness makes them ideal for studying dark energy, which dominates where matter is scarce. The Euclid Space Telescope will map millions of voids using their shapes and evolution to constrain dark energy properties. Voids are the universe's laboratories for studying repulsive gravity. The philosophical implications of voids are profound. Most of the universe's volume is essentially empty, with matter confined to a small fraction of space. We live on the edge of a void in a thin filament of the cosmic web. The universe is far emptier than our galaxy-rich neighborhood suggests. Emptiness, not substance, defines the universe's large-scale character. Future surveys will reveal the full extent of cosmic voids. The Vera-Rubin Observatory will detect billions of galaxies, mapping voids in unprecedented detail. The square-kilometer array will trace hydrogen gas in and around voids, revealing their true boundaries. We may discover voids even larger than the billion light-year supervoids known today. The question of the largest structure takes on new meaning when considering voids. Is emptiness a structure? If so, the largest voids rival any concentration of matter in size. The universe's largest features might be defined by absence rather than presence, emptiness rather than substance, void rather than form. Everything we've discussed so far, the great walls, superclusters, and voids, might give the impression of a static universe, like a frozen sculpture of galaxies. But the largest structures in the universe are in constant motion, flowing and evolving on scales that dwarf human comprehension. These cosmic flows, streams and collisions, represent dynamic structures that span billions of light-years and reshape the universe over billions of years. The Great Attractor isn't just pulling galaxies, it's creating a vast flow pattern affecting hundreds of thousands of galaxies across 600 million light-years. This isn't random motion but organized flow, like a cosmic river system with tributaries joining larger streams. The Cosmic Flows project has mapped these motions in detail, revealing that what we thought were separate structures are actually parts of enormous flow patterns. The dipole repeller discovered in 2017 adds another dimension to cosmic flows. Located in the opposite direction from our motion toward the Great Attractor, this vast void actively pushes galaxies away. It's not just the absence of gravitational pull, the void's expansion creates an effective repulsion. Together, the great attractors pull and the dipole repellers push create a cosmic flow pattern spanning over 1 billion light-years. Colliding galaxy clusters represent the universe's most energetic events. The bullet cluster, where two clusters collided at millions of kilometers per hour, created shock waves visible in X-rays spanning millions of light-years. The collision separated dark matter from ordinary matter, providing direct evidence for dark matter's existence. These collisions are structure formation in action, building larger structures from smaller ones. The El Gordo cluster, discovered in 2012, is another massive collision in progress. Nicknamed the Fat One, it's the most massive cluster known at its distance, 7 billion light-years away. Two clusters, each containing hundreds of galaxies, are merging at over 2 million kilometers per hour. The collision zone, glowing at 200 million degrees, spans several million light-years. But individual cluster collisions pale compared to supercluster scale dynamics. The Shapley supercluster isn't just a static concentration of galaxies. It's actively growing by pulling in surrounding clusters and galaxies. This creates infall patterns spanning 500 million light-years, with thousands of galaxies streaming towards Shapley's gravitational center at hundreds of kilometers per second. The cosmic web itself is dynamic, with filaments acting as highways for galaxy motion. Galaxies don't just sit in filaments, they flow along them toward the nodes where clusters form. The Virgo cluster, our local supercluster's heart, draws galaxies from filaments extending hundreds of millions of light-years. We can watch structure formation happening in real time on cosmic scales. Dark energy adds another dynamic element. While gravity pulls structures together, dark energy pushes space apart. This cosmic tug-of-war determines which structures survive and which dissolve. Structures smaller than about 100 million light-years are winning against dark energy, growing denser. Larger structures are losing, gradually dissolving as dark energy dominates. The turnover scale, where gravity and dark energy balance, creates a maximum size for bound structures. Currently at about 1.2 billion light-years, this scale is shrinking as dark energy strengthens. Future structures will be limited to smaller sizes, making our epoch special for hosting the largest structures that will ever exist. Baryon acoustic oscillations represent frozen sound waves from the early universe, but they're still detectable in galaxy distributions today. These primordial ripples, with a characteristic scale of 490 million light-years, create subtle density patterns that affect cosmic flows. Galaxies are slightly more likely to be separated by this distance, creating a cosmic rhythm in structure distribution. The integrated Sachs-Wolf effect reveals how structures evolve. As cosmic microwave background photons traverse the universe, they gain energy falling into gravitational wells and lose energy climbing out. In a static universe, these effects cancel. But with dark energy, structures decay while photons cross them, creating a net energy change that we observe as temperature variations. Cosmic downsizing describes how structure formation has changed over time. In the early universe, the largest structures formed first, fragmenting into smaller ones. Today, structure formation proceeds bottom-up, with small structures merging into larger ones. This transition, driven by dark energy's growing influence, marks a fundamental change in how the universe builds structures. The cosmic web's filaments aren't static bridges but dynamic streams. Gas flows along filaments at hundreds of kilometers per second, feeding galaxy formation at the nodes. The MUSE instrument on the Very Large Telescope has directly observed this cosmic gas flow, revealing that filaments are like cosmic arteries carrying matter to where galaxies form. Future evolution will dramatically reshape the largest structures. In 50 billion years, dark energy will have dissolved all structures larger than galaxy clusters. In 100 billion years, only gravitationally bound groups like our local group will survive. The Great Walls and superclusters we observe today are temporary features in an evolving universe. Peculiar velocities, deviations from pure cosmic expansion, map hidden mass concentrations. By measuring how galaxies move relative to the cosmic flow, we can detect massive structures even in the zone of avoidance blocked by our galaxy. These velocity fields reveal that structures larger than what we directly observe might be influencing cosmic flows. The universe's largest structures pulse with seismic waves from ancient collisions. When galaxy clusters merge, they ring like cosmic bells for billions of years. These oscillations, detectable in X-ray observations, can span tens of millions of light-years. The universe's largest structures are not only moving, but vibrating with echoes of past violence. Turbulence operates even on cosmic scales. Where cosmic flows meet, enormous eddies form, spanning hundreds of millions of light-years. These create mixing regions where galaxies from different streams interact, triggering star formation and active galactic nuclei. The universe's largest structures are not laminar flows but turbulent cascades of matter and energy. Time-domain astronomy reveals structural changes happening now. The Zwicky Transient Facility and upcoming Vera Rubin Observatory detect millions of transient events, supernovae, tidal disruptions, and active galactic nuclei. These trace real-time changes in cosmic structures, showing that even the largest features evolve on observable timescales. After journeying from galaxy clusters to cosmic voids, from great walls to the observable universe itself, we must confront a fundamental question. What do we actually mean by largest? Is it physical size, mass, gravitational influence, or something else entirely? The answer isn't as straightforward as it might seem, and different definitions lead to dramatically different candidates for the universe's largest thing. If we define largest by physical extent, the observable universe itself wins at 93 billion light-years across. But this is an observational limit, not a physical structure. Among actual structures, the Hercules corona Borealis Great Wall spans 10 billion light-years, over 1/10 the observable universe's diameter. Yet even this might be surpassed by undiscovered structures hiding in unexplored regions of sky. Mass tells a different story. The observable universe contains approximately 10 to the 53 kilograms, but most of this is dark energy and dark matter spread throughout space. The most massive, concentrated structures are galaxy clusters like El Gordo, containing the mass of 3 quadrillion suns, but superclusters, while less dense, contain far more total mass spread over larger volumes. Gravitational influence extends beyond physical boundaries. The Great Attractor influences galaxy motions 600 million light-years away, far beyond its physical extent. The Shapley supercluster affects cosmic flows over 1 billion light-years from its center. By this measure, the largest structures are those that bend space-time over the greatest distances. Volume presents another perspective. The cosmic voids, particularly supervoids like Eridanus, encompass volumes that dwarf any matter concentration. If we count emptiness as structure, then voids containing billions of cubic light-years of nearly empty space might be the universe's largest features. They define the cosmic web's architecture more than the matter-filled filaments. Coherence adds complexity to our definition. A structure implies organization, not just proximity. The cosmic web's filaments show coherent organization over billions of light-years, but are they single structures or collections of smaller ones? The giant ark's 3.3 billion light-year extent shows apparent organization, but we don't fully understand what maintains this coherence. Time introduces another dimension. Structures aren't static, they grow, merge, and dissolve. the largest structure today might not be the largest tomorrow. During cosmic noon, 11 billion years ago, different structures dominated. In the future, dark energy will dissolve today's largest structures. Should we consider the largest structure ever, or only what exists now? The hierarchy problem complicates our search. Galaxies group into clusters, clusters into superclusters, superclusters into walls and filaments. Where do we draw boundaries? Is Laniakea, containing 100,000 galaxies, one structure or many? The answer depends on whether we define structures by gravitational binding, coherent motion, or simple proximity. Dark matter structures might dwarf visible ones. Simulations suggest dark matter forms halos extending far beyond visible galaxies and filaments, connecting clusters that we can't see directly. The largest dark matter structures might span the entire observable universe in an invisible web. Should invisible structures count when determining the largest? Information content offers another metric. The observable universe contains roughly 10 to the 123 bits of information, according to holographic principal calculations. But how is this information distributed? Black holes, despite their small size, contain enormous information. By information density, the universe's largest structures might be its smallest objects. Causal connection defines physical structures. Regions that can exchange information form coherent structures. Those that can't are separate regardless of proximity. By this measure, structures larger than about 16 billion light-years are impossible. Dark energy prevents causal connection over larger distances. This sets an absolute upper limit on structure size. The multiverse hypothesis suggests our observable universe might be one bubble in an infinite foam. If true, the largest structure might be this foam itself, infinite in extent, containing infinite bubble universes. But can something infinite be called a structure? Does the question even make sense in an infinite context? Quantum considerations add another layer. If the universe is a quantum system, its wave function might be the ultimate structure, a mathematical object describing all possible states simultaneously. This wave function, if it exists, would encompass not just our observable universe, but all possible quantum histories. Emergence challenges our definitions. Just as consciousness emerges from neural activity without being localized in any neuron, cosmic structures might have emergent properties not present in their components. The cosmic web's pattern might represent an emergent structure more significant than any individual wall or void. The anthropic principle suggests we observe structures of certain sizes because only universes with such structures can support observers. The largest structure might be determined by the requirements for complexity and life rather than physical limits. We see what we see because anything else would preclude our existence. Future discoveries will likely revise our understanding. The Vera-Rubin Observatory will catalogue billions of galaxies, potentially revealing structures dwarfing anything known. The square-kilometre array will map hydrogen throughout the universe, possibly discovering invisible structures we've missed. The Roman Space Telescope will survey vast sky areas, perhaps finding coherent structures spanning the entire observable universe. The philosophical implications run deep. If the universe is infinite, there's no largest structure. For any size, infinitely larger structures exist elsewhere. If it's finite, the universe itself is the largest structure. The question reveals assumptions about the nature of existence, infinity, and what constitutes a thing. Perhaps the most profound answer is that the largest structure isn't a thing but a process, the cosmic evolution that creates and destroys all structures. From quantum fluctuations to galaxy clusters, from the Big Bang to the far future, this process spans all of space and time. The universe isn't just the stage, but the play itself, constantly creating new, larger structures. Our search for the largest thing in the universe has revealed that the question itself evolves as our understanding deepens. Each answer opens new questions, each discovery reveals larger contexts. The largest thing in the universe might ultimately be our growing comprehension of it, an expanding sphere of knowledge that, like the observable universe itself, grows larger every day while revealing ever greater mysteries beyond its edge. We've traveled from Earth to the edge of existence, from galaxies to great walls, from supervoids to the observable universe itself. We've explored structures so vast that light needs billions of years to cross them, discovered cosmic flows that carry thousands of galaxies like leaves in an invisible river, and confronted the limits of what can exist in our universe. Now, at the end of our journey, we're ready to answer the question, what is the largest thing in the universe? The answer is both simple and profound. The largest thing in the universe is the universe itself, not just as a container, but as a single, interconnected, evolving system of which you are an integral part. Every atom in your body, every thought in your mind, every star in the sky participates in this cosmic unity. The boundaries we draw between structures are human conveniences. In reality, everything is connected in an unbroken web of cause and effect, stretching from the Big Bang to the far future. Consider what this means. The calcium in your bones was forged in the heart of a massive star that exploded billions of years ago. The water in your cells has been cycling through cosmic clouds, comets, and oceans for eons. The energy that powers your thoughts came from the sun, which drew it from nuclear fusion, which became possible only because of the precise laws that emerged in the Big Bang. You aren't separate from the universe. You are the universe examining itself. This isn't mysticism, it's the literal truth revealed by modern astrophysics. The Sloan Digital Sky Survey showed us that galaxies are connected by invisible dark matter filaments. The cosmic microwave background revealed that every point in space shares a common origin. Gravitational wave detections prove that space-time itself ripples, carrying influences across billions of light years. We live in a cosmos where everything affects everything else, where the largest structures emerge from the smallest quantum fluctuations. The observable universe, all 93 billion light-years of it, operates as a single system. Energy and information flow through cosmic filaments. Gravity reaches across billions of light-years to orchestrate the dance of galaxies. Dark energy provides a universal backdrop against which all structures evolve. Even the voids, those enormous empty spaces, play their part by pushing matter toward the filaments and nodes where galaxies form. But here's what makes this even more remarkable. This largest of all things is growing. Every second, our observable universe expands by thousands of cubic light-years as light from ever more distant regions finally reaches us. Every second, new galaxies cross into our observable sphere, adding their stories to our cosmic narrative. The largest thing in the universe is getting larger, and we're here to witness it. Yet paradoxically, while the observable universe grows, the number of galaxies we can potentially observe shrinks. Dark energy is accelerating cosmic expansion, pushing distant galaxies beyond our future horizon. We live in a special epoch when we can still see the cosmic web in all its glory, still detect the Big Bang's afterglow, still trace our origins. Future civilizations will see a simpler, lonelier universe. This makes our moment in cosmic history precious beyond measure. We're the universe's memory, recording its structure and history before evidence vanishes into the accelerating darkness. Every observation we make, every photograph from Hubble or Webb, every map of cosmic structure preserves information that will someday be unrecoverable. We're creating the only record of the universe at its most complex and beautiful. The structures we've explored, from the Hercules corona Borealis Great Wall to the cosmic voids, aren't separate from us. We're embedded in the cosmic web, residents of the Laniakea supercluster, citizens of the local group. The same gravitational forces that shape billion light-year walls shape the orbits of planets where life might emerge. The same dark energy that drives cosmic voids affects the ultimate fate of every atom in your body. When you look at the night sky, you're not seeing distant, unrelated objects. You're seeing family. Those stars share your origin in the Big Bang. Their atoms were forged in the same cosmic processes that created yours. The light entering your eyes has traveled for years, centuries, or eons to complete a connection between you and its source. In a very real sense, seeing is a form of cosmic touching across the vastness of space and time. The largest thing in the universe includes not just space but time. The observable universe is a four-dimensional structure extending from the Big Bang to the far future. Your life traces a unique path through this structure, your world line, that will never be exactly repeated. You're not just in the universe, you're a thread in its four-dimensional fabric, connected to every other thread through the complex weaving of cause and effect. This perspective transforms how we see our challenges and opportunities. Yes, we're tiny compared to cosmic structures, but we're the only known parts of the universe capable of comprehending these scales. Yes, we're temporary. Our species has existed for a cosmic eye blink. But in that eye blink, we've discovered the universe's age, composition, and fate. We've seen structures our ancestors couldn't imagine and revealed connections that span billions of light years. Every time scientists discover a new cosmic structure, they're not just adding to a catalogue, they're revealing new aspects of this single, vast thing we're all part of. The giant arc, the South Pole Wall, the cosmic voids. These aren't separate objects but features of our shared cosmic home. Understanding them helps us understand ourselves because we emerged from the same processes that created them. The search for the largest thing in the universe has brought us full circle. We started by looking outward, seeking ever larger structures external to ourselves. But the journey revealed that we were inside what we were looking for all along. The largest thing in the universe isn't out there, it's right here, all around us, within us. We are components of the largest possible structure, participants in the grandest possible story. As you go forward from this moment, remember that you carry the universe within you. Your atoms have circled the galaxy, your molecules have been part of countless other forms, your energy has flowed through stars and nebulae. You're not a small, isolated being on a tiny planet. You're a focal point where the universe has become conscious of itself, a place where the largest thing in existence achieves self-awareness. The next time you feel small under the night sky, remember, you're not beneath the universe, you're part of it. Those vast structures we've explored aren't foreign territories but neighborhoods in your cosmic home. You're as fundamental to the universe as any galaxy, as essential as any star. In discovering the largest thing in the universe, we've discovered that we ourselves are facets of this ultimate cosmic jewel, each reflecting the whole from our unique perspective. The largest thing in the universe is the universe itself, and you, yes, you, are an irreplaceable part of its immensity, beauty, and ongoing story. In seeking the cosmos, we find ourselves. In finding ourselves, we discover we are the cosmos. This is the ultimate cosmic perspective. We are not observers of the largest thing in the universe. We are participants in it, expressions of it, and bearers of its consciousness. The universe hasn't just created large structures, it has created beings capable of appreciating its largeness. And in that appreciation, the universe achieves something perhaps even grander than size. It achieves meaning. If you are still watching, please make sure to subscribe and give a thumbs up. And if you enjoyed this video, I am sure you are gonna love this other one at the left side of the screen. Does time stop when you hit the speed of light? In this video, discover the real science behind time dilation and what happens to time as you approach light speed. Explore the mind-bending consequences of traveling near light speed, the twin paradox, and what it means for space travel, causality, and the nature of reality. See you there.